Right, awesome. So I'm Kate Burgess. I am the PI of the ANGSA team out of NRL, and as Brittany gave an amazing introduction, we focused on the cold curation of these samples and doing TEM, attempting to find where these solar wind volatiles that Paul talked about as being so important from a remote sensing point of view. I don't know that you can see these volatiles that we found using remote sensing, but this is looking for one of the places that the volatiles end up stored. So as Brittany said, we're focused on the space weathering aspect of this, and specifically from the solar wind, thinking about where the hydrogen and the helium is. This is a TEM image, HADAF, so high angle annular dark field, analogous to backscatter. Brighter is denser. You can see the nanophase iron grains here. This is an agglutinitic glass that then has a space weathered rim on it, just as a cool picture. And so as Brittany said, we're looking for the hydrogen and the helium. The hydrogen, as Brittany noted, has not previously been found in silicates on the lunar samples, but we do have examples where this technique has worked previously in an IDP. And we have previously found the helium in an ilmenite and phthalate phases. So we're focused on the cold samples because there could be a large difference in the rate of diffusion given the difference in temperature. And so we wanted to see if that was enough to retain measurable amounts of volatiles. So I will focus here on data from Fib samples. These were prepared in a kind of traditional manner. We did not keep the samples cold during sample preparation. So they all have had maybe a day or so by the time we analyzed them in the microscope, in addition to the 3 weeks after their return from the moon before they were initially frozen. And so here's an SEM image and then of the grain itself and then the extracted Fib section. And here is that Fib section. You can see all of the kind of classic space weathering features. There's a vapor deposited rim. There's several different populations of nanophase iron, and there are vesicles. This is an olivine grain. So these are the kind of weird planar vesicles that we see often in olivine that Brittany talked about. And what we see in one of these vesicles is then signals of both the hydrogen and the helium. And you can see it in comparison to the IDP data. These are not huge signals. This is not a lot of volatiles, but it's real, it's there, it's clearly different from the background and the surrounding material. We have direct comparison for this sample of another Fib section from the same soil of the room temperature stored. Again, an olivine, same shape vesicles, same size range of nanophase iron. And we looked in as many vesicles as we could find in both samples, and several times in the frozen samples saw helium. Did not see that in the non-frozen sample. So as hard as it is to get any kind of statistical buildup in TEM, this is a pretty good example of just what we're seeing, that we find it in the frozen and we just don't see it in the room temperature stored samples. One other grain that I found that was really interesting. So this vesicle has a signal that appears right around 8.5 eV. And at first you get really excited that this looks like the energy gap for water. Turns out it is molecular oxygen. And so I was a little bit disappointed. I was like, oh, this isn't water. And then I was like, well, this is actually really kind of interesting. Where do you get molecular oxygen in all of these reactions that's so clearly trapped within this vesicle? And this is not a frozen sample related thing. I know this has been seen by others in room temperature samples very recently. And so this is, you can see the very sharp 532 EV peak there in the oxygen K edge. And then the excess peak kind of right at 540 that you see in the blue and the red compared to the black is indicative of this molecular oxygen signal. And so this vesicle is a little different. It's between kind of a thick, I don't know if you would call this a vapor deposit versus a melt splash kind of rim, and the olivine itself in with a lot of nanophase iron. And so it's kind of interesting to think about where this oxygen comes from. In the literature, the previous time this has been pointed out is actually in an IDP again, which in an aluminosilicate you wouldn't necessarily think has a relationship to space weathering, but it also is not related to beam damage, just the way it's localized to the vesicle, and doesn't change now with repeated measurements. And so, really trying to think through where this oxygen could come from. Right from the beginning of looking at these rims, Keller and McKay did point out that these vesicular and amorphous rims often do show oxygen superstoichiometry. And so there's certainly something happening within this process that gets you liberated oxygen. And it seems interesting that we are trapping it, and not all these vesicles are directly necessarily related to hydrogen and helium. And then just this grain was very interesting. It had some structure and damage to it that I was able to pull out. And I'm still trying to figure out if I'm seeing shock effects and what exactly. So the it's a large MADF this time image, and so it's picking up the same things but with slightly different contrast between different densities, materials. And you can see this kind of weird feathering structure to the olivine. And then on the right, there's a HADF, a map of the 532 EV oxygen peak, and then a map showing the iron oxidation state where red has Fe3 plus present. And so there's oxidation to the rim material at the top, but then also kind of associated with the weird contrast and the presence of this oxygen-oxygen bond or molecular oxygen peak. So we're able to use this technique to start to understand other things about what's happening in these grains. If there is some shock, if, just off the view of my fib section, there was some kind of, crater or something like that I didn't see. And so that's what we're picking out, is this pre-existing structure. I thought this was just really interesting. I'm, again, still trying to figure out what to do with finding this kind of linear pattern in the olivine. As Brittany noted, these low loss features all end up looking a lot the same. Determining what's water and what's not is very hard. But it looks like there may be defects in this olivine that are showing oxygen-oxygen excess bonds. And for reference, when we're looking at these energies, we're looking at energies rather than wavelengths. And so something in this range is equivalent to the VUV. So to wrap up, I got my 2-minute warning, I must have gone through fast. We are seeing the presence of some hydrogen species and helium in these vesicles in the silicates in the frozen samples. And this has not previously been seen definitively in the Apollo samples. We're also seeing this oxygen trapped in the vesicles and in the olivine structure, and we're working out if this is a space weathering process or some other process, and just how common it would be to have these vesicles formed by something besides the solar wind. And as Brittany noted, then these samples are highly reactive to the electron beam, and that is very affected by the pre-existing structures in the crystal, but then also much more so than in the room temperature samples and the standard samples that we've looked at. And then just this image on the right, I can never resist it. This is a nanoparticle on the surface of one of my grains that the bright is ilmenite, and there's some nanophase iron in it. And it's just very cool. So